electric motor used to move a variable load, and the motor is connected in series with a battery and an ammeter. So the ammeter is going to measure the current through the motor, and the battery is going to be applying or supplying a fixed potential difference. So let's have a look back. Sorry, have a look at this. So this is always a little bit confusing. What we've got to work out is why the motor current is very small when the load is actually load is zero. So I'm struggling a little bit. So here we go. First off, what I'm going to do is just kind of talk you through the idea or the principle. So if I have a look at it, what we're going to have is, let's just consider a quick plot. And this plot is going to be a voltage versus the speed of the motor. Okay. Now in terms of the battery is always going to supply a fixed voltage. So it's always going to supply a fixed voltage. Therefore, you can imagine that we've got that here. So this is our applied voltage from the battery. All right. Now, you're happy with this by this point, or you should be happy by this point, that a motor and a generator are the same physical thing. The motor, you apply a current, which causes a force, which causes it to spin. A generator, you apply a force, which causes the armature to spin, which induces an EMF. Now, this means that when a motor is running, it's also inducing an EMF. And it's inducing, the induced EMF is in the opposite direction to the supplied EMF because of Lenz's law. Now it's actually called, or quite often called, the back EMF. So if you could imagine what happens is, if the motor isn't spinning at all, there's no induced induced back EMF. Equally, but as you speed up, and I'm not saying this would be perfectly linear, but as you speed up, you can imagine that, or you can accept that, the idea that your induced back EMF will increase. Now, what that actually means is your voltage across the battery, across the motor, is going to be reducing, because here your voltages are maximum, and then what's going to happen as you go through, be about there, draw that down. So what's actually going to happen is the actual applied EMF, for a way of describing it, to the motor is going to be reducing. So if we think of it let's try and write this out to give you a better idea. So the applied voltage from the battery minus the induced back EMF is going to be, that's going to be a voltage, and so then it's going to give you I times R, where I will be the current through the motor or around the circuit. So when we're going really fast, in fact our maximum speed, if there's no friction, what's going to happen is, at maximum speed, if there's no friction, your applied EMF, applied from the battery, minus your induced EMF, or your induced back EMF, would be zero. Which means, by definition then, your current would have to be zero at that maximum speed. Now, let's have a look at this. So they want us to talk about why there'd be a very small current when you've got zero load. So when zero load is applied, the motor will spin very quickly, or very fast. So it will induce a large back EMF. Now if there's a large back EMF, pretty much the same as the applied from the battery, you're going to have a very small overall current across the motor. Therefore, there will be a small current through the motor, because the battery, less the induced EMF, is pretty much zero. If there was no friction, the only thing that would be slowing it down or meaning it reaches the maximum speed is this induced EMF. Hopefully that makes sense. Thank you very much.